Okay, yeah, as I was saying, I'm Gianluca. I'm a research engineer at TeamStudy, which is a company that, in a few words, is doing trying to use reinforcement learning for solving industrial optimization problems. We have different use cases. So we, for example, optimize for train schedules, but also, as I'm going to present to you now, we also use deep reinforcement learning in our product, Deep PCB, for placement for PCB design, placement, and routing. In this presentation, I will briefly discuss with you what the PCB is and how we basically like solve the problem, which is quite complex. And then at the very end, I will give you like a short demo on how we integrate with MCP our tool with the chat, so you can actually use our product with just natural language. So PCB in stand for printed circuit board, and it's basically like most of the electronic boards that you can find in your electronic devices, from your PC to like your smartwatch and so on. And the design of such like complex boards consists in these three stages. So at the very beginning, you have the schematics definition, where like normally hardware engineers like define the electronic components that need to be like defined for a specific functioning. Then there is the placement, which is basically taking the equivalent physical components of those like electronic ones and is placing them inside an electronic board. And you have to follow specific design constraint. For instance, you want your USB-C connector of your iPhone to be at the bottom of the device, for instance. Then you have the routing. So like to have the actual functioning, you need to connect those components and let the electronic, like the current flows, basically. In the PCB, we focus on the last two stages of this process, so like the placement and the routing. But let's see why PCB is quite like a difficult problem and why we need to kind of optimize it. Uh, in the automotive industry, for instance, you have boards of like quite big dimension, but also like not as big as you can expect. You can find like boards of like thousands of nets that you have to connect. The problem there is that like an hardware engineer that needs to do like to do the connection and the design could take from like days to actually weeks also for the complex one to do this design. And you can imagine that like the demand here is quite high. We are surrounded by electronic devices, and if we have to wait like every time a week or even more maybe to do the design, these like really don't match the market that we are in now. And the problem is very complex because like you have in a realistic boards, you have from like 100 to 1000 of components to place, and you need to like route like thousands of nets to connect those components. And so just to give you some numbers, if you think about Go or chess, that are like quite easy optimization problems, you go for like possible configuration at 10 at the power of 40 or 10 at the power of 170. But here we talk about like big numbers because we take like we can consider possible configuration at 10 at the power of 10,000. So like it's quite big. The problem is a massive combinatorial problem, and the problem is not just like the design per se. It's also because like you need to actually like print the board at the very end, and so like you need to test some like physical constraints. And if a designer has to do that, you have like you realize that like your design was not proper at the very beginning, you need to like remove a wire and do the thing again, and this take hours or days in addition to the original one. Of course, there exist heuristics to kind of like speed up this process, but the problem with heuristics normally is that like they prefer speed over quality. And if you imagine a problem with like this kind of complexity is quite difficult. Here we can see like as like A star, for example, with the shortest path, is not even able to route these very easy circuits on your right. And it's very easy. Like you have just two nets, two components, grid word, and that's it. But like here, the problem is that like the shortest path is not the optimal solution if you route those nets sequentially. And imagine then when you have like even more complex design constraints. So with Deep PCB, we basically want to provide products to the hardware engineers, support to the hardware engineers, and we want to provide like them so an easy to use product, but also something that is like that provides solutions that are quite that are favoring quality, not just speed. And here we can see like an outboard engineer can basically like use our tool. He can upload the board in like different formats, and you can decide to place a route or like do the both of them together. And you start like seeing like the improvements. You start to see like quite fast like the solution proposed by the AI, but also like the outboard engineer can change like the board, so he can stop and get other solution later, or you can like delete one wire as I'm doing here, and you want just to reroute that part of the board. You're able to do that. And so that's really increased the speed. But maybe you're wondering what is like under the hood. I spoiled myself a bit at the beginning, so it's not LLM, but it's like reinforcement learning. I mean, we are using LLMs, MCP specifically, to do like the combination of a chatbot and our tool, but like the engine behind is reinforcement learning. And reinforcement learning is quite powerful in this case because it's a framework of AI, which basically, instead of learning from data that are provided to the agent, it learned by collecting those data itself, by interacting in a simulator. And that's quite powerful in situation where you have like such big configuration and such big possibilities. Because like you can maybe stress your search for data into area of your search space in your like solution space that like maybe were not like couldn't be provided by a human, or this is very powerful also for generalization, because since you're optimizing a specific objective, you are basically not relying just on the training data, but you can use these things that you learn also when you find situation that you haven't encountered during training. And that's quite powerful, like in such a huge like space of configuration. The other very important prerequisite actually here is that you have a very reliable and fast simulator, and that needs to be realistic. And that's like basically what we develop as well at InstaDeep. We have a simulator that can perform like 4 millions of steps per second, or like on the order of millions of steps per second. And it's very realistic because we build it with collaboration with our hardware engineers, basically. And so like the solution at the very end is like, as I said at the beginning, placement and routing. The two problems have different objectives. And so like you basically like do the things like sequentially. And you want to do the placement, you start from a board, like the board that we find here in the left, with all the with some component inside, maybe because they are like fixed component, and some other components on outside. And you have a specific objective, which can be like, for example, you want a filter to be very close to the source of the signal because like you want to filter out the noise as soon as possible. And these are defined in our reward function, and basically like the agent try to optimize for this objective. Then once you have the board that is like fully placed, or you can get like a board that is already placed by like an hardware engineer, for example, you can do the routing. So like the routing is just like the connection of the wires, like of the components with wires, and need to follow very, very hard like physical constraints. So the interesting part of this problem is that it's not just a game where you have like to connect these dots with like different colors, like and that's it. Like you get like the board fully connected and you're done. Now here you have a lot of physics going on afterwards because you need to print the board afterwards. And so you have to respect all the manufacturability constraint and and you need to preserve the signal. So it's very important that your objective is not just speed. So provide a solution as fast as possible. We need that, but we need to focus on quality as well, because like otherwise you spend like millions of euros like for nothing basically. And we were able to achieve this quality with speed as well. For example, with this board, you have like an hardware engineer that can take like 2 days or even more to do the complete routing, and we were able to do the same routing or like similarly quality routing in 3 hours, in just 3 hours. So you can see that like here the speed up is significant, and so like we are able to help the hardware engineers to like keep pace with the demand of the market. So here I will present you like the demo. So you can see like how I use the chatbot just to make. We decide to do this integration to make the even easier to use the tool. So here I ask the chatbot to basically route specific board. I upload the board. We use FileBin, but you can use whatever you want. You get directly like the link to the board and to our product. where you can see the board, you can investigate it, you can zoom in, zoom out, and like search for all the components you want. You can like modify the board, and you can see the solution that like come quite fast. You can see like all the progress. You can check this progress on the chatbot as well. And I was doing that here, for instance, in this case. So you can see like how many wires, how like long the wires are in the board, how many vias. You can investigate like the planes in the board. Like this is a quite complex board with like 4 layers. And you can check like all the physical constraints such as like the clearance and stuff. Then you can go back to the chatbot. You can like I don't know, check other metrics, but also like if you're done, you can stop the process and just download the board that you completed. And it's quite helpful because like you're not just targeting like professionals, but also like for example hardware engineering students. They can use this tool like quite easily. And here we're gonna see like as I did like the same for placement in this case. You just need to upload like more files because like you need the constraint placement that I mentioned before, and you basically like get the same feeling. Like you can get the board, you see like the initial solution with all the placement, all the components outside, and then you initially see like all the solution that came out and come out. Then you can of course like stop again and get the board again. So this was a presentation to just give you like an idea of like what is our product and like how we use reinforcement learning, not like just to train LLMs, but also like to solve some like combinatorial optimization problems for industry, such as the PCB design. And I hope that you enjoyed the talk and thank you. And yeah, I'm here for any question.
If you have any question, raise your hand.
How do you transform some references into the reward function? So like if you want, for example, a filter to be close to the source, how do you transform that into, I thought that this was the MCP integration where the engineer could say, oh, I would want like this code to be somewhere there, and then translate that into a reward portion. But otherwise, how do they do it in the software?
Yes, thank you for the question. No, like this like kind of interaction that you were talking about would be nice. The problem is that like you should like modify the simulator every time, and that's kind of like time intense. So basically, like we try to collaborate as much as possible with our hardware engineers to define and design the reward function as like proper as possible. So the agent could already like check by like investigating in the simulator, check the reward and like optimize for the reward. Of course, like the design engineering of like the reward function is quite like important, of course, because you optimize that function at the very end. But yeah, that's what we normally do. Like we define the reward function and design it.
That's like a best practices reward function.
Exactly. With a lot of like knowledge from like hardware engineers. But yeah, it's yeah, we collect the best practices. We get the reward function.
Have you tried into the mass production on all some of the example here, all the mass production, whatever you talk about here, into a real product?
We have the product is already like online.
Yeah.
We haven't like have a situation yet where like you actually like print the board. But we have feedback from the other engineers and they were quite happy by the results. And this is kind of like one thing that is also important here. Like seems like you spend a lot of money when you print the board. Like the hardware engineer, you need to build trust on the hardware engineers, and that's what kind of we are targeting. So like if the hardware engineer trusts our product, we kind of like are already safe in saying that like maybe they're gonna print it.
Yeah, because most of the routing and suggestion constraint is all done by the CAD tool anyway. So
Yeah.
so have we ever guide you guys to compare whatever you simulate or whatever you modify against the existing CAD tool? Because the CAD tool have a lot of experience around it.
Yeah. We actually did some like comparison between like you're talking about the auto router of the CAD
Yeah,
tools.
from the Allego,
Yeah,
whatever.
yeah.
They have all the experience and most importantly, they have all the device characteristic in it. Basically, when you design a board, they can literally can simulate whatever the real thing happens because you have component characteristics.
Yeah.
And your side, if you can have a simulation telling people on the ball how good is it, how bad it's gonna be. It would be probably
Yeah, actually, we're working on like having like a simulation as well. But the problem with the CAD tools, I would say, is that like they follow heuristics, and then therefore, like for example, like they are of course like more complex heuristic than just the one that I showed you, like the shortest path. But still, like you cannot generalize to any possibilities. So like maybe like you have an algorithm engineer that like prefer some specific designs, and so like the CAD tool is built for like the user of that CAD tools. We kind of like try to generalize to like multiple possible situations. So like in a sense, like learning the objective is more like powerful and generalizable than the CAD tools. And indeed, like when we went to like conferences of like PCB designs and stuff, they were surprised because like they tried to use our like product and it was better than the CAD tools in like providing the solutions. So I'm not sure if I answered, but like
We'll see.
yeah,
Cadence for Siemens might be interesting.
yeah, they were collaborating.
If you saying it better than it.
Yeah.
Thank you, Gianluca.